Recording from now. It's recording, so it's sharp 5. Okay, that's good. Thank you so much, everyone, to coming to our seminar. It's like a short lecture thingy, right? It's going to be from on the topic of from electrons to material properties that Professor Fung from Castle University has agreed to teach us in the 6 weeks that he is visiting us. The class is very much structured. It starts with some theory, and then toward the half of the class and the end of the class, we are gonna talk about how we can put this theory into action and really calculate material properties using the very first principles. Without any further ado, I'll leave the presentation to Professor Fung.
Yeah, thanks, Andrew, for the nice introduction. Title is clear. So today we will work with the classical foundation of mechanics. So we will not have to do anything with quantum mechanics today. This will start, I think Thursday is the next day. Yeah. But yeah, this is the foundation, so that you get a feeling for the more theoretical view on the world. And we will start with these classical mechanics. Hamilton's principle is probably most important to start with classical mechanics. So we consider that we can describe our entire system with a function, which includes the positions of each particle in our system. So these are Q. The derivatives of the locations with respect to time, which I denote this way as Q dot. Second derivatives are then with 2 dots at the top, and the time. This has everything in it what we need to know our system, to characterize it. And however we want to move our system, it will move in a way that this integral, which is the action integral, is getting minimized. So this means that always the path is chosen where the least action is necessary. From here, we can build the entire picture of classical mechanics. This is where we start from. The minimal action which is necessary to move from the position A, where we are at time t1, to a position B, where we are at time t2. And whatever happens, happens with minimal action. So we vary so that it gets minimal. This is the general variational principle. And then we just need to apply the variations. So we vary the coordinates and the velocities, and we integrate everything over time. Now this integral can be integrated partially, which yields this term and this one. This term is within the variational principle, so this means that this variation should be approaching 0, so that this term is simply getting 0. What remains is here. Our variation in Q can be arbitrary, so that this can only be 0 if this part inside the brackets becomes 0. this directly yields the Euler-Lagrange equations. These are our equations of motion. If we can construct a Lagrangian, which is this function, L, we can solve the equations of motion and get a real motion at minimal action. Clear so far? Okay.
So just a question, so Q is the Cartesian coordinate
It
or
can
just
be
a
any
general
kind of coordinate. It can be Cartesian coordinates, it can be curvilinear coordinates, polar coordinates, whatever we want. It always holds true. If I want more specific coordinates, I typically use R, which means distance coordinates in a Cartesian space. And I will tell you when we see this. So from the Lagrangian, we can have a look at some conservation laws. Our assumptions from classical mechanics are that time is homogeneous. It is not isotropic, because it matters if you go either into the future or into the past. Space is homogeneous and isotropic. These are our boundary conditions for our classical world. So with homogeneity of time, we see that our derivatives, we can just derive this, and we see that this term can easily be rewritten. Q dot dot is dq dot by dt, so that we can complete this. And what we also see is, you know how to derive something. If you derive this becomes q dot times this derived by time plus q dot derived by time times this. And this is exactly this term. Yeah? Just a product rule for differentiation applied. In this case, we just go the reverse way. If we subtract our Lagrangian, we obtain 0. Because this is nothing else than effectively our Lagrangian again. So Lagrange minus Lagrange is 0. If the Lagrangian doesn't change, then the energy is conserved. Or the action is 0. So we see that within this formalism we can prove that energy is conserved. You cannot create energy out of nothing, you cannot eliminate energy out of nothing. Homogeneity of space, a little bit different. We vary our Lagrangian with respect to the Cartesian distance coordinates. This variation is infinitesimal, so we can write it as epsilon. We know this from mathematics. So this part should be 0 if we conserve, if space is homogeneous. But this can only be 0 if this part can be 0, because epsilon can be arbitrary. So this holds true for any of these. We can derive with respect to time and sum over all the derivatives, or we can sum over all velocity derivatives and then derive by time. It is just the same, and it is all 0. So if we are adiabatic, which is important, so nothing may enter, nothing may leave, this part is constant, and we define this part as the momentum of our system. From all these, we can get a clear idea of how our Lagrangian looks like. This is pretty simple. Just here. Because this can only hold true if our Lagrangian is a difference of kinetic energy and potential energy. And the kinetic energy is a function of velocities, and our potential energy is, in the cases where we deal with, a function of the coordinates. You can also have potentials which are functions of velocities, but in our case, we just deal with this. This is a typical classical case. So keep this in mind. And kinetic energy, we all know, 1/2 mv squared. So if we derive the Lagrangian with respect to the velocities, what we obtain is the parts. 1/2 m squared derived 1/2 mv squared derived by v is mv. And this is the momentum. Because if you derive the potential by the velocities, it is not the same variable, you obtain 0. Finally, isotropy of space. This means if we rotate our Lagrangian system by an infinitesimal angle, or by any angle, the properties of the system must not be changed. It does not matter how our system is oriented in space, it has the same properties. So for example, you throw a ball, it doesn't matter if you throw it forward, backward, anywhere else. Gravity has the same effect. So this means that our variation is then a variation of the angles for velocities, as we do not derive this variation by time. It's just is a function of velocities. So as I said, the Lagrangian does not change when the system is rotated. And this means that the variation of the Lagrangian is 0. Same formalism as we had. Now we had already our definition of momentum, so that we can write this. Yeah? This equation is just the same here, if we take this into account. So we enter this into this equation, we obtain this. And now we have these parts. Vector products of Cartesian vectors and temporal derivatives of the momenta and velocities and momenta. Again, we know this product rule, so we can put this into this much easier form. Again, the variation is arbitrary, so this cannot be 0. This means that this part has to be 0. And this means that the angular momentum is conserved, because this just describes the angular momentum. So we see homogeneity of time yields to the conservation of energy. Homogeneity of space yields to the conservation of the momentum, and isotropy of space yields to angular momentum conservation. Until here, all is fine.
So basically, you are saying that this Lagrangian that you are defining here is somehow another way of writing Newton equations, right?
Yes, we are here within our Newtonian world, but with a more sophisticated mathematics.
And what's the I mean, like, we are doing a lot of math here, but what's the advantage of doing this much of involved math?
The good thing is that we have now our Euler-Lagrange equations of motion. So whenever we can construct a Lagrangian, we have a straightforward way just to follow the recipe of solving these equations of motion. So it's whatever problem we just need to be able to formulate it as a Lagrangian. If we do not formulate it as a Lagrangian, if we cannot do this, we fail.
It's more straightforward to do the calculations when you express it this way.
The mathematical solution of these equations of motion is much simpler than the original Newtonian way. But in principle, we are still in Newtonian mechanics. Perhaps a nice exercise. Anyone who wants to volunteer? It's pretty easy. It's just to prove that when we are working with a Lagrangian and we have a particle which faces no potential, that it moves with constant velocity. Anybody wants to do this on the board directly? No?
Maybe you do it and then we correct
Yeah.
you if you made any mistakes. Right?
So, okay.
But can you use another color because it's very hard to see it from here.
Okay, yes. Some,
I have a couple of them.
I have some here. Black and blue.
This is blue.
blue? Blue is nice. So, okay, this is our equation of motion. Our Lagrangian has simply the form because there's no potential. So let's see what our equations of motion say. We have this derivative. Well, we do not have q as a variable, so this derivative simply is 0. Correct? Next, this derivative. Well, 1/2 mq dot squared is simply mq dot. And now we derive this with respect to time. Well, in principle, we have it already in our equations of motion. So what we see is this is the equation of motion, which we have, right? This is 0, this stays, so this must hold true. Mass doesn't change, so we can use any mass. So what in the end stays here? Maybe I'm just writing it so that everyone can see it. So what we are keeping is the derivative of velocity with time is 0, and this means we have constant velocity. It does not change over time. So you see this is Newton's first law, simply derived with the Lagrangian formalism. So this is the advantage how we see it. Okay? I could also prove that the action principle, so that the second and third laws hold true. This is even easier. In this case, we would just say that, well, we would just bring this on the other side. Right. So, this is the action principle, the reaction principle. Because this is a force. This is then something equal to a force. This is mass times acceleration. And this is minus. We directly get it. The acceleration, the movement of the particle is in just the opposite to the force. So you see, it's a very powerful formulation of Newtonian mechanics. You see, you're just straightforward. You go into it, you enter your Lagrangian, you calculate, and you get your result. So let's have a little fun. Central force. The central force is defined in a way that we have a potential which is just depending on the distance. Whenever I'm writing bold, I mean a vector or matrix, and when I'm not writing bold, I mean a scalar. So we have the radial distance r. This is where our potential depends on. And as it is a force, we need a vector. This is just by this distance vector divided by the distance. This just gives us the vectorial information. So in principle, it can move anywhere in space. We have just a point which is the origin of our force, and this particle can move anywhere around. This yields a spherical problem, but we know that the angular momentum is conserved. So what does this mean? If we have a conserved angular momentum, we have to move in a plane, because if we leave the plane, we change the angular momentum. So in this case, we would violate the conservation of the angular momentum. So already we have some information. And this makes it a little bit easier. So we are just applying polar coordinates in 2 dimensions. Sure, when we are moving in a plane, we don't need the third dimension. Then we take the origin of our coordinate system so that it is identical with the origin of our force. And let us say we have our force originating from another particle. We introduce a reduced mass of both particles. Then we formulate our Lagrangian. Well, in polar coordinates, we can transform from Cartesian to polar. So we have our distance and we have our angle. We have an angular velocity. It still needs to be the correct dimensions. So it is angular velocity is then distance by angle. And we have our potential. As a central potential, it is just depending on the distance and not on the angle. What we may see is that this Lagrangian is not explicitly a function of the angle. Right? It is a function of the distance and of the temporal derivatives of the distance and the temporal derivatives of the angle, but not of the angle itself. This is an important property because such coordinates, which are not explicitly in the Lagrangian, are cyclic coordinates. And the Lagrangian, derived with respect to cyclic coordinates, is always 0. not only for the cyclic coordinate, but also for the temporal derivatives. So this makes things a little bit easier. So our momentum is then generalized. As we are in polar coordinates, this becomes then identical to the angular momentum. Of course, we're in an angular world, so we have an angular momentum, and we know that it is conserved. So it stays constant. Now this can be used and can be inserted into this equation. And from there we can have the total energy, which is all kinetic energy and our potential energy. However, as we see here, well, this is a constant, mu is a constant, and we have a distance term. So in principle, we can formulate a kind of effective potential, okay? So you have nothing to do with velocities here. So this is a part, it is a static world, and this, as it is static, it is part of the potential. So we have kinetic energy and some kind of effective potential. Energy is also conserved so that we can find an expression for our velocities, which is pretty easy. But this is a derivative. Yes, but you see it? Here we have it. We just change the form of our equation and we get a nice expression for our velocities. Interestingly, the velocities depend on the distance. Now, dr with respect to dr derived by dt. Well, we can formulate this then as well. And we have all of, if we have all of this, we go back to where we started. Just a second. Yes. We go back where we started. Now we have et in terms of dr. And we can get a nice expression for our angle. And if we are smart, we have this constant so that it starts at phi equals 0. We are free to choose it by boundary conditions, and we can just start with phi equals 0. Here's our effective potential energy again. It's just depending on the radius and on nothing else.
How do we find the total energy related with the previous equation in the previous slides? The energy E, which is, yes, no, this one, the previous slide.
Yeah.
This one, equation 5, F5,
Yes,
right?
yes, this is, in principle, we have our Lagrangian, which is T minus U,
Right.
and the total energy must be T plus U. The sum of
It's a
kinetic
total internal
and
energy,
potential
right?
energy. Yes.
Okay.
So this was our original expression for T,
This is a T, right?
and then we had minus U. So for the total energy, we just need to change the sign to potential energy, and we get the full expression.
So this is the total energy definition, but
Yes.
but then when I look at the Lagrangian L, which is always defined like T minus U as well, right?
Yes,
Okay.
and here we just go, if you just change the sign of U, you automatically get the total energy.
Okay.
So we are here, and this is important because this is the general solution for the angular part of a central force potential. Whenever you are facing a central force, you can use this solution. Always. And so you should keep this very, very well in mind. It can help you with many problems. You just need to insert the correct expression of the potential energy, and you can solve it. Because everything else, total energy, sure, okay, you also need the correct expression for this, but everything else is just well defined.
And why the second term, the last equation, is part of the potential energy? Because that the second term on the right hand side should be part of the original phi,
Yes,
phi,
yes.
right?
Yes, but this is, what we see is that we have an angular movement.
Yeah.
And this part does not include any angle.
Well, mathematically, it could include.
Mathematically, we just say all parts depending solely on the distance are summed into some kind of potential. So this is a true potential energy plus this term, which also is solely depending on the distance. And
Yeah,
then we
from
say
this
it is
equation, yes.
It is an effective potential.
Right, but if you compare with one of your previous equations on the second term, it comes from the kinetic energy.
Yes, yes, it does. And in principle, this is a part of the kinetic energy. But for our mathematical purpose, we just sum it together with the original potential. We call it an effective potential.
But that's it under assumption m must be a constant.
Yes, yes. This only works as m if m is constant. So without conservation of angular momentum, we could not do this. But here this is constant, so r is the only variable which is left. And then we can say it is some kind of effective potential. What the particle is feeling when it is moving in orbit or whatever it is. Okay, this is not really practical, but there is one very nice practical problem, Kepler's problem. You have a planet and a star. The star is a massive object, the planet is smaller, and so we can sum the gravitational energy just like this. We have this alpha, which is all the gravitational force that is coming, that is experienced by our particle. As we had before, we can formulate an effective potential. The angular momentum is still conserved, and so we can form such an effective potential. And, as I told you, keep this one in mind. We have our potential. So we can just enter and solve the integral. And we get a solution for phi. Well, this looks a little bit complicated. And from there we cannot directly say how the movement would look like. But now we define, please do not take this for a momentum. I just call it for mathematics, P and E. And if we have this, our equation looks like this. This is just an ellipse. Or let us say it is an ellipse if our total energy is always lower than 0. Because our effective potential energy looks pretty simple. This is R. This is U. Okay. Until here, it should look, typically it gets above. So, if we are inside this region, the particle has not sufficient energy to leave. If it gets up here, it is repulsed. If it is here, it is not directly bonded. And this yields 3 solutions in principle. We have our central object, which is giving the force. One solution with a repulsion looks like this. The orbit solution can look like this, or it can be a total circle, it doesn't matter. And then we also have the third solution, which is looking like this. These are 3 solutions, and they are applied. The fact that we can be repulsive with gravity is used when we are sending space probes to worlds far away. We are using solution 1 and 3. This one accelerates, this one prevents a collision. But we have to be fast enough. If the kinetic energy is too low, we will be captured. If it is far too low, we will crash into the planet. So you see, it can be, this is a complicated problem. You see, it can really be tricky to get an easy solution. If you do not get the idea to define these, you will never get your elliptic solution. Or you get it, but you do not see it. And if you do not see it, then you're missing what is happening in reality. Of course, nowadays you can just put it in a computer and see what happens. But in principle, this has been solved with Lagrangian formalism already 200 years ago. Because the people just didn't have computers, so they had to rely on this. And you can see the length of the semi-major axis. And what we see is it solely depends on the energy. It does not depend on anything else. Whereas the semi-minor axis also depends on the angular momentum. So it really matters if we want to know how large our radius, our orbit is, to understand how much energy we can have in this system. And the angular momentum defines how eccentric our ellipse is. And you see, the more angular momentum, the less eccentric we get. The less angular momentum, the more eccentric we get. 0 angular momentum just makes a straight movement. We just crash. we have seen all the.
Very quick question. So you plot this U versus R curve. Is
Yes.
this the equation come from one of your previous ones or not? This is kind of very specified, right?
Yes,
There's a
this
potential
is
in front of
directly
R.
when we plot the potential.
Yes, so is K1, I don't think K1 should satisfy this equation.
No,
This-
K2.
K2, oh
This
yes,
is
that's
the
right.
effective potential.
Yeah,
With K2, we get this part where we are repulsive.
okay, great.
So with K1 alone, we would not see the repulsive
Right.
part.
So in reality, whenever we use a potential, that should be U or U effective then, later
Yes,
on.
this would be.
U effective, right?
Right. So here you see the importance of the effective potential.
Basically only a mathematical trick, right?
It is a mathematical trick. Of course, this angular momentum part of the effective potential. If we put it into the kinetic energy, we would obtain the same result. But mathematically, this is much more easier to see why we get a repulsion. If you would have it in the kinetic energy, you would think, okay, why is there a repulsion? But here we can have such a nice sketch of our potential where we immediately understand why we have repulsion. It just helps us to understand what's going on in the system. So, back to the beginning. We already did this to our Lagrangian. But we also have the definition of momentum, how we can rewrite. We derive the Lagrangian with respect to the coordinates. This yields a force. The force is the same as the derivative of our momentum with respect to time. The dq part stays. This we've already seen is just the momentum, and this part stays. Now we can do some mathematics. We have a look at this. We can look at the total differential. We write this, and we obtain this nice part. Well, what we have here is 2 times the kinetic energy. Right? This is mv and this is v. So we get mv squared. We subtract our Lagrangian. So this is 2t minus t minus minus v. So it is t plus v. This is the total energy. We can write it like this. And now what we do is define the function that describes the total energy. And you see, it's just an expression of the energy, and we call this expression of the energy as a function the Hamiltonian. This is Hamilton's function. It is just a function describing the energy of our system. What we see is that we transform a function of velocities, coordinates, and time to a function of momentum, coordinates, and time. Now you may ask, what is the advantage? Any ideas?
Derivative.
That's derivative.
Derivative with respect to time.
Instead of second derivative, we have
Yeah.
first derivative.
Yes,
So
right.
it makes life much
Exactly.
easier, right?
Yes, yes, right.
That's really good.
This makes stuff much easier, and of course, we are no longer depending on constant mass. Lagrangian has constant mass. The Hamiltonian, not necessarily. In the classical case, this doesn't matter. As soon as we are getting relativistic, the Hamiltonian formulation is much more easy to handle. You can even do a relativistic Lagrangian, but it is a horribly complicated thing, because you need to work with something which is not made to describe the problem.
But how did we get equation 24? I forgot from the previous slide, right? How did-
24?
Yeah.
It's just a definition.
Oh, this is a
It's
definition.
just a definition. We define the total energy as the Hamilton function. So we just say this is a total energy, and we just define this is Hamilton's function.
Oh.
So Hamilton just said, I do not want to have this t minus u. I want to have I directly want to see my total energy function. And this is a trick. And with this, we can easily transform those. So you can see that this is total energy. If you have velocity and you integrate it the momentum, and at the same time you have the opposite integral for minus momentum with velocity, you are in principle getting the full energy. Because this is a force integrated with respect to coordinates, and this is a velocity integrated with respect to momentum. So this is kinetic energy, and this is potential energy. Yeah? We know the potential energy is minus the derivative of the force. The force is minus the derivative of the potential energy, according to Newton's third law. So this is potential energy, and this is kinetic energy. And the sum of both is our total energy, of course. And here we have the same description, just in terms of the Lagrangian, which is involved. So this is total energy. The Hamiltonian describes the total energy as a function. So the H must be this, which is just what we have here. Much more fun with Hamiltonian mechanics is that we can also easily derive these nice little equations. These are the canonical equations, and they replace our Lagrangian equations of motion. When you work with it, you will see how easy it is. You have your total energy function, your Hamiltonian. You derive with respect to momenta, and you get velocities. You derive with respect to coordinates, and you get your forces. Just directly out of it. No complicated thing. So it is much, much more easy to handle. I think as a homework, I have something nice for you. Just that you can learn about the advantages. So you have a potential. Potential. R squared. This is an harmonic oscillator. And the system is, you have one particle with a mass, you have a second one with the same mass. They are connected by a spring, with the spring constant K. And the distance is R0 in equilibrium, and it is R0 plus R out of equilibrium. Okay? And with this, you can work. Find an expression for the equations, for the motion of this system, both with the Lagrangian and with the Hamiltonian. So in principle, what you should derive is something like R of t. This is the task.
What's the deadline? For the homework? Next session? I mean, like,
Next session is pretty tight. What, can you make it to the next session?
No.
I mean, in principle, it shouldn't take that much time.
because for the next session, they need to understand Hamiltonian, otherwise they're not gonna be able to
Yes.
follow.
Yes. Can you make it to the next session? I think so. Especially with these, it's easy. If you can't make it, try these first and then go to the Lagrangian. So this is more important to have it with the Hamiltonian.
So for the mechanical system, this Hamiltonian H is always the same as the total energy E?
Yes.
But then why we're creating two terms then?
Well, because we still have oscillations in the kinetic and the potential energy.
Uh-huh.
So the two terms of it are not constant all the time.
But that's fine, if even under that condition, E is always equal to H. If that's the case, I'm still confused why we're having two terms or two
Just
symbols.
H, we have E of t, E of the time,
Yeah.
and we have here this as a function of our phase space and the time. So if we integrate over all of time, then we are constant.
Okay.
But we are not constant if we are looking at infinitesimal distances in time. So this is our movement that we obtain. So we have an idea of how to construct the energy and what the total energy over time should be. But we do not have an idea how it develops in terms of kinetic and potential energy. And especially not how it develops in terms of the momenta and of the positions in space. I mean, this is what we want to know. If you have, for example, you take an airplane and integrate all of its moves over time, over its entire lifetime, and it has flown all possible routes, then the integral will more or less tell you that it's in the center of Earth. So it doesn't help us to understand how it moved. And this is why we need this function. So we are not after the total energy so much, but more after the movement. So that we can say we started at a certain time and at a certain position. How does the system develop? Where does it go? When you understand this here, this is very important to understand this, that we want to have a precise position and a precise momentum or velocity at any specific point in time. So that when we know our initial conditions, where our particle or let's just say object is located, and we know its momentum, and we know its angular momentum, and we know the potential energies it faces, then we can just run the simulation and we know exactly how it will develop, where it moves, at any point. If it moves different, then probably we've forgotten some potential energy term. But as long as we have the full potential energy and the initial velocity and the initial mass, we know how it will develop. Exactly. This is classical physics. We know exactly where it is at any point if we know where we started. We should keep this in mind very well. Because on Thursday, I will show you another one where we will not be able to tell about all of this. We are still using a Hamiltonian, but in a by far different situation. But here, it really works like this. You know where we start, you know our mass, you know our initial vector where we are traveling, you know the potential energy. Finally, I want to show you some really important stuff. If we add another parameter, it may be an external force or whatever, it doesn't matter what it is, then we can extend our Lagrangian without any problems. Yeah, it's just derivative of the Lagrangian with respect to this parameter, and then we integrate over it. We can also just enter this to the definition of the Hamiltonian and how we get it from the Lagrangian. And we see, well, it's almost the same. It's now just t plus v and not t plus u and not t minus u. And we are not getting plus this parameter term, but minus. If you like, you can prove it. The funny thing is, if we combine both, we see that the derivative of the Hamiltonian is just minus the derivative of the Lagrangian. Now, as I told you, the parameter can be everything, even time. And now if we remember just in the beginning where I showed you that the Lagrangian derived by time does not change, means that we conserve energy, then the minus doesn't do anything about it. So this is 0, and then this is also 0. So this is a general rule that applies to any parameter, but if we enter time, we can prove that also the Hamiltonian is conserving energy.
What does it mean to add another parameter?
Say we have our velocities, we have our coordinates, and we are interested what happens if we add some external force, for example. Then this is also a part of the component. We can have a force which is time dependent, and we want to add this to our equation. Then we do not know yet how it really affects the equations of motion. And this is just a term to correct it for the new parameter. Or in this case, we are just going to an explicit treatment of time. So whatever it is. It can also be a relativistic correction.
What correction?
A relativistic correction. So this may also work. But this is much more easy with to do this with the Hamiltonian than with the Lagrangian.
Can lambda be pertaining to non-conservative forces as well?
Yes, principle. Okay. Kind of 1 hour of buffer, so obviously that's not necessary. This is good, because I think the quantum world is worth much more explanations. But I think that for today this is sufficient so that you all have this classical picture and you can understand how to have a theoretical look on the world and how to still have the opportunity to apply this to practical problems, like Kepler's problem, like the harmonic oscillator. And I think this is very important to know that it's not just theory for the paper. You can really do stuff. You can prove general properties of space-time with it. You can prove that under our boundary conditions, just from our assumptions of how space-time is formed, homogeneous time, homogeneous space, isotropic space, we can derive all of Newtonian mechanics. With the Lagrangian, we can also do this with the Hamiltonian. And this is very, of course, if it holds true for the Lagrangian, if this holds true, and this is just 2 times kinetic energy that we add, it must hold true for the Hamiltonian as well. Are there questions left? They may appear.
So one of the purposes you're introducing this Hamiltonian is you want to use this kind of concept or other formulations for quantum mechanics,
Yes,
right? Later on.
yes.
So we are in the traditional this Newton's mechanics, right?
Right.
So Hamiltonian kind of theories can cover all the Newtonian mechanics.
Yes.
But on the other hand, we cannot just simply use our traditional classical mechanics to describe the quantum mechanics. Is that one of the reasons you are introducing?
But interestingly, we can apply at least the translation from a problem, from a practical problem into theory. What we can do now here for the Hamiltonian mechanics.
Yeah.
We can go a very similar way in quantum mechanics.
Okay.
So especially the potential energies are typically very easy to transform into quantum mechanics because they are just looking the same as they do in classical mechanics. But what I can already tell you is in quantum mechanics we do not have this luxury to know exactly the position of each particle if we at the same time know the velocity or the momentum. This is not possible.
So that's why, you know, when we use any engineering principles, there's always 2 ways to describe the response. So we typically use forces, and then we end up with the differential equations, and we can solve for any displacement or something. On the other hand, we can always use the energy approach and to get the same result, because these 2 can be equivalent, right? As long as the total potential minimization approach works.
Exactly.
So it's really up to us whether we want to use whatever one of the 2 method.
Right.
So now back to the quantum mechanics. So probably we can only use the energy approach, right?
Yes.
As you said, the position may not be, what is the criterion we called? Uncertainty?
Uncertainty.
Yes.
Right.
Heisenberg uncertainty.
Right. So okay, so then we better know more about the energy approach.
Plus,
or Hamiltonian.
we even don't have continuous changes in
Yeah, that's right.
energies in quantum mechanics.
Okay.
Quantum mechanics, we have some very interesting problems that when we change potential energy, we can only change that it jumps. So We travel at a certain velocity, average velocity, an expectation value, which by the way is not the 100% answer how fast the particle is. And we change the quantum state and we immediately change the velocity. So it's a change in light speed. So it just takes a very small amount of time to change it. And here we can just continuously add potential energy or kinetic energy. So when we just slightly add more and more kinetic energy, we can get a wider orbit for a particle. In quantum mechanics, we cannot do this. We have the correct energy to add to get to the next higher orbit, or we don't get there. But you will see more of this in the coming lectures. And you should learn this energy, this view on energy as a function of the system. Because this view you will have it every time in quantum mechanics. More questions? Good. Okay.
Highline textbook.
In principle, of this part, I would recommend Lemmer and Lifshitz. So they have a very good text, but I think it's also translated in many languages. Also in English.
Also,
Yeah, this-
Griffiths is really good.
Griffiths.
Yes, yes.
And would you share your slides with us so we can?
Yes,
take
sure, sure.
And like a cheat sheet, right? And so we have the email addresses. We are gonna send out the lecture notes to everybody. Right?
Yeah. And if I find time to make a good script out of it, probably within the next few months, if I do.
In this class, has everybody worked with HPC? Is there anybody in this room who hasn't worked with HPC?
What do you want to do with HPC?
We are going to have some simulation. We are going to run some simulations.
Oh, it's gonna be
So for that thing, I mean, like when we go, like in the probably 4th or 5th week, we are going to run some quantum mechanics calculations, and for that we need people to run simulations on UCI HPC.
What software will you use?
We are going to use Quantum Espresso, right?
Espresso or VASP.
Or VASP. We are going to see.
Very good.
Good. So I try to actually make you a temporary username on my own server, so you can actually run simulations on my computers.
I think everyone who's a UCI student can have access to HPC.
Access to.
Yeah, you can ask for a user.
Okay, so I mean, like, if you haven't had access to UCI HPC, then you should contact the manager who is there, Joseph Farron, and ask to make you a username and a password, right? And then probably on one of the sessions, we are gonna show you how to log in, run one sample job, analyze the results, so it becomes really intuitive.
Maybe.
Good. Thanks for coming.
See, this is exciting. Look, you know all that. There is a hypey guy over there. No, we're gonna go. Oh, yeah, we're gonna go.
They just left halfway through the.
Have you seen Fazin?
If we already know. No problem. Have you seen Yeah, no, I can go ahead.
Oh.
Yeah.
I'm going to the
You have to
conference
know
next
that I
week.
have been working in the field for some time. Pretty rusty. So when you were talking
But
about.
how's the speed of the lessons? I mean, like today, he talked about both Lagrangian and Hamiltonian.
I think it's okay.
It's okay, he's
And
not going too fast.
another
right?
part was that once you brought it back to like elementary physics, this is mv squared, derivative, this is what you're gonna do. That once you move from, you're in the two domains, in the elementary domain and you go into the higher level, that was good.
So just give them something they remember.
Yeah.
And then they understand. Because otherwise, I mean, for me, like quantum is something very natural. Hamiltonian even more. It's just like, yeah, there's kinetic energy and, well, okay, nice, but nothing which I think much about. I know how it's looking like, but
Yes, it's just is something that you read and eat and breathe, so it's more easy for you, for us.
We are still looking at the velocity and momentum. It says we have to always think about it. Momentum is mass times velocity, right? You have to think about it. It doesn't come
For
naturally.
me, I just like one and one, two. This is for me.
Okay.
That's the level that I do now. If I run out of fingers, I have to use my feet. I mean, that's it.
for me, momentum is what I get when I integrate a force by time.
Yeah.
Or when I derive energy by velocity. This is momentum.
Yeah, so you go with the definition of impact.
Yes.
All right, I have a student waiting for me.
Okay,
So
good.
I'll see you guys,
On
I'll see you
Thursday.
tomorrow, but I'll see. I'll be
And he's
back
gonna be
on-
around here, so he.
Yeah, I'll come to the lecture on Thursday.
Sure. Anything else? Don't forget the homework. I'm joking.
I wouldn't forget the homework.
Will you talk about
Let's go.
Yes, Happy Hop will be next week. So when we come to many body systems. So this next lesson will be just introduction to quantum mechanics, some postulating the stuff. Next week I will start with just in brief the solution of the hydrogen atom, and from there I will go to atom rock, directly starting on Tuesday with atom rock and the entire Thursday.
So we talk about, for example, exchange coordination, energy.